T324 Tut5. In this tutorial we will present the main factors contributing to the characteristics of radio propagation. Basically, radio signals propagate from the transmitter to the receiver. However, the real world of Earth, skies, buildings, car, and so greatly affects how this propagation takes place and introduces a large number of issues which determine the characteristics and limitations of an application. So, in this tutorial, I shall briefly describe some of the main factors which contribute to the characteristics of radio propagation and some of the differences between the various frequency bands. First of all, let's start with the inverse square law. Basically, when you move further away from a transmitter, the power you receive becomes smaller. Radio receivers have a limited sensitivity. They need a certain signal strength in order to recover the information it contains. Any decrease in the signal limits the maximum distance over which the communication is possible, and so knowing the factors which cause the radio signal to decrease is important. In this part, I am going to consider how the received power varies with distance in what is perhaps the simplest situation in free space when there is no other matter nearby to affect propagation between the transmitter and receiver. I shall also assume that the transmitter and receiving antenna transmit or receive equally in all directions. They are called isotropic antenna. Radio waves emerging from an isotropic antenna also travels at the same speed in all directions, but the difference is that they are not usually constrained to move on a plane surface. In free space, a radio signal spreads out in 3 dimensions, so rather than a circle. As you can see in the following figure, that shows 3 successive positions of an expanding wave. The spherical expansion has been cut away to show more clearly what is happening to a small area. Because the wave is spread over a larger and larger surface area, the wave expands, so the power is spread over a larger area. In the figure, a square area is shown at distance d equal 1, at distance d equal 2. This has expanded out of to be 2 times 2 equal 4 squares. At distance d equal 3, it has been expanded out to be 3 times 3 equal 9 squares. So if the radius is doubled, the surface area expanded by a factor of 4. If the radius is tripled, the area expanded by a factor of 9, and so on. Now imagine a receiving antenna that is the same size as this small square at d equal 1. If this antenna is now moved at d equal 2, then it's only capturing 1/4 of the power received at d equal 1. It's moved at 2. If it is moved to d equal 3, then it's only capturing 1/9 of the power at d equal 1. Since the power of the wave is being spread over a larger and larger area, the power received over a fixed area must be decreasing. In fact, the received power with 1/d square. This is called the inverse square law of radio propagation. So, in free space with an isotropic transmitting antenna, power received by a fixed size of antenna varies according to the inverse square law. In free space, I repeat. However, communication on the surface of the Earth are not always as simple as this, although the inverse square law must operate. In addition, there is the ground to consider: the atmosphere, the weather, the mountains, the valleys, people, vehicles, any other objects on the path between the transmitter and receiver. This can all alter the propagation of radio waves, sometimes dramatically, and the effects are described in the following parts. One of these factors is absorption. For terrestrial communication, radio waves always travel through some form of matter, whether it's the gases of the atmosphere or the walls of your house. This can cause wave energy to reduce even more quickly than under the inverse square law alone, and so limit the maximum range of signals even more. The absorption through the atmosphere is due to the presence of water, vapor, and oxygen, and the way these effects vary with frequency is shown in the following figure. The horizontal scale is frequency from 10 GHz to 400 GHz on a logarithmic scale. The vertical scale represents attenuation of a signal and runs from 0 to 50 dB per kilometer on a linear scale. You may or may not have come across dB before. If so, you will probably follow the graphs, explanation, and activities in these sections that involve dB without any problem. I remind you that decibel is the unit that is equal 10 log 10 the ratio, okay, of power. In this case, if decibel are new to you, then you should review the slides presented in the previous session, and there you can find there some exercises that could make you familiar with this unit. So the use of decibel is very common in wireless literature, as we have said last time. So it's very important that you become familiar with this unit. However, let me reassure you that decibel do not involve any advanced math or calculation. Their use is to simplify only the analysis of wireless systems, not to complicate it. So if you want to read on these sections before we continue with the factors that affect the propagation of radio waves, you can go back to the previous to the slides of the previous sessions and continue with the following presentations. First, note that up to nearly 50 GHz, the amount of attenuation does not appear to be significant on this graph. Right back to very low frequencies, the attenuation is low enough not to cause any significant problem with long distance terrestrial links. Second, as the frequency increases towards 400 GHz, the amount of absorption rises steadily with a number of peaks. The peak at 60 GHz and the small blip at about 100 GHz are caused by the oxygen in the atmosphere. The two higher peaks are caused by water vapor. Because of the high attenuation at these peaks, the maximum propagation distance for radio frequencies in these regions is greatly limited. Above the frequencies plotted here, the attenuation coefficient continues to rise. For radio waves above 300 GHz, the losses are so great in practice that they are of no value for terrestrial communications. Lastly, note that figure 9 is for clear air. Rain, snow, fog, dust, and other atmospheric effects can all increase the losses by significant amounts. Absorption and other losses by building materials such as bricks or wood are also significant and increase as the frequency goes into gigahertz range. The overall picture of these materials is very complicated. Every material has its own amount of attenuation which varies uniquely with frequency. However, To give you a general idea, some typical values for two building materials are shown in the following table. The two materials are glass and concrete at two frequencies, 1 GHz and 60 GHz. You can see that the attenuation coefficient in dB per meter this time through both materials increases dramatically with frequency, and that concrete absorbs much more than glass. So finally, I would just like to point out the positive side of signal loss through the inverse square law, absorption and other effects. Because radio waves decay with distance of propagation, then frequencies can be reused in different places without interfering with each other. This is the principle behind cellular phone systems, which allow a far higher number of simultaneous users than non-cellular systems. It makes feasible all the short-range devices such as Bluetooth headsets and remote car locking, and it allows reuse of broadcast frequencies on a national or regional level, thus using the limited spectrum much more efficiently. In free space, radio waves have an uninterrupted path between transmitter and receiver. By analogy with visible light, this is called a line of sight. On Earth, there can still be a line of sight if the transmitter and receiver are close enough, but the line of sight is often limited because of the two main factors. The first is the curvature of Earth. This is so that the curvature itself can become a barrier to reception. This is exactly the same as the visual horizon, which puts a limit on our vision of distant terrestrial objects. The second factor limiting line of sight is the presence of obstacles in the path, such as mountains, forests, buildings, and vehicles. If these attenuate radio waves, then they will affect reception. It's no longer a line of sight when, say, a building which absorbs most of the radiation at certain frequency is in the way. Again, taking an optical analogy, the building is casting a radio shadow in which the signal will not be received. The simple view would imply that radio communications can go no further than the horizons, and that a building will cut off all reception beyond it. But there are a number of other effects which make radio communication possible around the globe, and which can smooth out the effects of shadow. The next parts describe the main effects. Reflection. You are probably familiar with the reflection of light from smooth surfaces, such as polished metal, glass, glazed tiles, and so on. This is described as specular reflection, with the key property that the angle at which the light is reflected from the surface is the same as the angle at which it impinges on the surface. This is shown in the following figure. Since radio waves are just another form of electromagnetic wave, they too can reflect from appropriate surfaces, including the ground, buildings, and vehicles. An important point to note is that reflection is much less effective if the reflecting object is smaller than a wavelength. So reflections from buildings and vehicles are much more important for the higher frequencies than for the lower ones. Also, even a metal mesh will reflect as long as the gaps are smaller than a wavelength. Reflection can be beneficial if reflective surfaces are in the right place. Then radio waves can be deflected away from the blocked line of sight and be received from a different direction, as shown in the following figure. However, reflection can be also a problem. There are many situations in which an antenna receives a combination of line of sight and reflected signals, such as that illustrated in the second figure. Since the path length for the reflected signal is longer than the direct path, the line of sight signal combines with reflected signals that are slightly delayed in time. This delay can cause the waves to cancel each other out. The following figure shows the effect of two equally sized waves arriving at the same point, which could be the line of sight waves and the reflection, or two reflections from different objects. In the following figure, the two signals are in phase, with each other in the first figure, so that the peaks of one correspond to the peaks of the other. These two signals reinforce to produce an even bigger combination. This is called constructive interference. In contrast, in the second figure, part B, the figure shows the effect of a small delay between the signals of one half of one period. In this case, the peaks of one correspond to the throat of the others. Here, the waves simply cancel out, leaving nothing. This is called destructive interference. A slightly different effect can occur in the reality, of course. So we have just presented here the two extreme cases, and what we call here is inter-symbol interference. All these effects are called multipath interference, or just multipath, and have been one of the biggest problems in achieving reliable coverage with mobile phone systems. Another factor is scattering. So, for example, if you shine a torch in a smoky room, the beam is revealed as light is scattered from the tiny smoke particles in the air. Similarly, light shining on a raw surface is scattered in all directions, allowing the surface to be seen from any angle. In just the same way, radio waves can be scattered from appropriately raw surfaces, from small objects such as leaves and road signs, and from particles in the atmosphere. Usually the word scattering is applied to the effect involving objects or features which are smaller than a wavelength. The key feature is that waves are scattered in many directions. Other factors is refraction. When light passes at an angle through the boundary from one medium to another, its direction of travel is changed. This process is called refraction. It's an analogy with the radio waves that could traverse also two different mediums. As for diffraction, this is a less well-known phenomenon, but one which is common to all forms of wave. Let's look to the following figure. In the first part A, it shows a wave heading towards an opening in a barrier. This could represent water waves, light waves, sound waves, or radio waves. The behavior is broadly the same in each case. The distance between the lines in the first part represent the wavelength, while the direction of propagation is indicated by the arrow. As you might expect, the part of the waves which reaches the opening passes through, while the rest is stopped by the barrier. The region behind the barrier is therefore a shadow region, which no waves reach. However, if you look carefully at the diagram, you can see that some of the emerging waves spread very slightly into the shadow region. This spreading is caused by diffraction of the wave at the opening. The amount of spreading of the waves is determined by this of the opening relative to the wavelength of the wave. All the effects described before lead to a very complicated picture of radio wave propagation in many typical situations. A receiver will receive a line-of-sight wave together with components that arrived after refraction, scattering, and diffraction from various terrestrial objects. These waves together comprise what is called the space wave. All these components of the space wave can contribute to multipath effects. In a rural environment, ground features, trees, animals, fences, and vegetation all contribute to the space wave. In an urban environment, there may be no line of sight to the transmitter, but instead waves are only received by reflection from buildings and from the ground, scattered from road signs or growing leaves, and diffracted around corners. The following figures show an example of a city street showing reflected, diffracted, and scattered waves propagating around corners. These effects change dramatically from place to place depending on the wavelength. So, for example, reception of a mobile phone signal in a moving vehicle can vary over quite short time scale, possibly leading to errors in the data or interrupted service. In any complex environment like this, received signal power varies for many reasons, including movement of the transmitter or receiver or changes in other elements of the environment, such as passing vehicles, rain, or trees moving in the wind. This variation of signal power in time or in space is termed fading. There are a large number of computer programs available to predict the pattern of radio reception in any given environment. These are based on various propagation models, which are simplified mathematical models of the many effects that are found in reality, including reflection, refraction, diffraction, and scattering. These programs tend to be most accurate for a particular type of environment and for a particular frequency range. The complex and varying urban environment is a particular challenge to model. However, modeling and measurement show that a good rule of thumb for such a complex situation is that the overall loss of signal power with the distance d follows 1 over d power 4 relationship rather than 1 over the inverse square law of free space. However, fading and multipath are not all bad news. Techniques are being developed not only to combat the effects of fading, but also to use multipath in a positive way to enhance the transmission, as we will see in the coming parts. You can try here to solve these exercises about the propagation in urban or rural area. We'll talk about MIMO in more details in the next sections. Basically, frequencies below 30 MHz are also subject to the same propagation effect of reflection, refraction, diffraction, scattering, but the observed behavior in this part of the spectrum is quite distinct. As you move down in the frequency through the HF and MF bands, the wavelength becomes huge comparing to the size of buildings and vehicles that have such an effect on higher frequencies. So the structures that begin to affect propagation are much larger, such as hills, mountains, even the curvature of Earth and the structure of the atmosphere. In particular, there are two ways in which radio waves propagate in the VHF bands. They dominate their use. These are sky waves and surface waves, which are presented in the following. The atmosphere consists of a mixture of gases, mainly nitrogen, oxygen, water vapor, argon, and carbon dioxide. The amounts of these gases reduce as you go up through the atmosphere. However, between about 60 km and 700 km above sea level, there is a very distinctive region called the ionosphere, which is characterized by a very large number of ions. These are formed when ultraviolet and other high energy radiation from the sun is able to ionize gas molecules. In other words, to detach electrons, leaving a mixture of positively charged ions and free electrons. Because the ionosphere contains many of these charged particles, radio waves are affected. For the microwave frequencies of the previous part, the ionosphere is largely transparent. They travel right through it. However, for low frequencies, the effect is for an upwardly traveling wave to be bent round until it's traveling back down to Earth. In the following figure, it shows what happens. The important practical point is that waves can propagate long distances beyond the horizon by refracting once from the ionosphere or by bouncing along in a series of hops between the ground and the ionosphere, as shown in the following figure. This form of propagation by means of ionospheric refraction is called a sky wave. At lower frequencies below 3 MHz, another form of propagation becomes the dominant one. This is a special form of propagation called a surface wave, which essentially propagates close to the surface of the ground because it follows the curvature of the Earth. It allows some radio signals to be propagated beyond the line of sight horizon and An exaggerated view of this form of propagation is shown in the following figure. Together, the line of sight wave, the surface wave, and any reflections from the ground are called the ground wave. Thickness in the VLF-HF bands can propagate extremely long distances, as we have said. Very large number of national and international transmission in this low frequency mainly aimed at portable devices. The limitations with higher frequencies can be summarized by the following 2 points. Higher frequency bands are all more or less limited by line of sight. Long distance communications are not normally possible. Interference at lower frequencies. Distant transmitters are more likely to cause interference. Fewer opportunities to reuse frequencies at a local level compared with higher frequencies. Transmitters need to be spaced over distances corresponding to countries or continents. Frequencies are comparatively low. This leads to the available bandwidth is very limited. This is the case of lower frequencies. To get a reasonable number of channels into the medium and long wave broadcasting bands, each is restricted only 9 kHz. The main method of modulation that is used in these bands is AM. I will talk later in more details about the modulations. These factors put a practical limit on the quality and reliability of broadcasting and communication, particularly in the MF and HF bands. However, there are moves to enhance the quality and reliability in this region. In particular, there is an international consortium called Digital Radio Mondiale, which is already broadcasting using digital modulation techniques in the LF, MF, and HF bands to minimize interference and loss of service and increase the information capacity of channels. This system is aiming to combine the long range and technical simplicity of the lower frequency bands with quality approaching that now found only in the VHF bands and above. At the beginning of this part, we have seen that radio waves were produced by an oscillating electric current in the transmitting antenna, and that they then go on to generate small electric current in the receiving antenna. The roles of the transmitting and receiving antenna are crucial to the success of radio communication. A properly designed antenna will generate a much larger signal than will an arbitrary piece of wire. Let's start with the fundamental form of antenna known as dipole antenna, which is illustrated in the following figure. Like most antenna, this can be effective either as a transmitting device or as a receiving device. A key property of the dipole is its length. If the length is half the wavelength of the radio signal, then the antenna will resonate at its frequency. It effectively becomes tuned to this resonant frequency, and the efficiency of converting radio waves to electrical signals and vice versa is very high. The efficiency falls away at higher or lower frequency, although it resonates as well at frequency which are tripled 5 times, 7 times, etc. These are called the odd harmonics frequencies. If the dipole is half the wavelength, then it's known as the half wavelength or lambda over 2 dipole antenna. A more familiar form of antenna is the vertical rod or wipe antenna, as used for FM reception in cars and for many other common wireless applications. It turns out that the length of such antenna is equal to lambda over 4. One side of the connection is referred to as the ground plane, which often means the surface that the antenna is mounted on. If the length is less than lambda over 4, then although the received signal strength is reduced, the performance is often adequate in many practical situations. The bandwidth of an antenna can be made wider or narrower than that of a simple dipole by using more complicated designs and by connecting to its suitable electronic circuitry. While many applications such as single frequency transmitter work better with a sharply resonant antenna with a narrow bandwidth, other applications such as wideband receiver require a wide bandwidth antenna. An important property of an antenna is the way in which their sensitivity varies with direction. A vertical rod will radiate equally as well in all horizontal direction around it. This is termed an omnidirectional radiation pattern. Note that such an antenna is not isotropic. Do not make a confusion between isotropic and omnidirectional antenna. Isotropic radiate equally in all the 3 dimensions, and omnidirectional antenna transmit, radiate or received equally in all horizontal direction only. The magnetic field, electric field, and direction of propagation are all perpendicular to each other. or to one another, like three edges of a cube which meet at a corner. The electromagnetic wave is the grouping of these electric and magnetic fields which are oscillating in time with each other, but which are perpendicular to each other and to the direction of propagation. Although the electric and magnetic fields must be perpendicular to each other, these pair together can be oriented at any angle around the axis of propagation of the wave. The direction along which the electric field is oriented is called the polarization of the wave. For radio waves propagating parallel to the ground, the case when the electric field is also parallel to the ground is called horizontal polarization. If the electric field is perpendicular to the ground, then it is vertical polarization. Although any angle of polarization is possible, usually radio waves are delivered polarized to be either horizontal or vertical. Orientation of the transmitting antenna. The angle of polarization is determined by the orientation of the transmitting antenna. The direction of the electric field is parallel to the direction of the current flow. Vertical antenna will produce vertical polarization, and of course horizontal antenna will produce horizontal polarization. Receiving antenna will respond best to a polarization that is parallel to it. So vertical wipe antenna usually mounted on a car will respond best to a vertically polarized radio signal. Same for horizontally polarized signal is better for broadcast transmission to house rooftop receiving antenna. When FM broadcast began in the VHF band, a horizontal polarization was chosen to maximize reception with a rooftop antenna. The problem is that when we have poor receptions, for example in cars, to solve this problem, transmitters were modified to transmit both polarizations so that mobile users and the other users who already had a horizontal antenna could all be satisfied. This is called mixed polarization and is used in many applications to maximize the reception of a wide range of users. So it uses both polarization, and the receiver will receives the one which is more suitable with his position. As for polarization diversity, it's possible to send two different signals. Here we have two different signals, one with each polarization and using the same frequency channel. So two differently polarized antenna as the receiver will then respond separately to these two signals. This polarization diversity is another method to increase the data that can be carried by a given radio channel. So we should distinguish between mixed polarization and polarization diversity. Problem addressed by wireless system designers are strong pressures in many systems to raise the data rate, fading and other multipath effect, interference from other users, and increasing number of users competing for limited available bandwidth. Some of the most important emerging technologies to deal with wireless design problems involves the use of multiple antennas, methods which exploit the difference between signals sent or received by different antennas are generally called diversity techniques. So let's take firstly the case of receiver diversity. So if two receiving antennas are spaced apart by more than a quarter wavelength or so, then in a multipath environment the space waves received by the two antennas are likely to be significantly different from each other. The simplest way to take advantage of this is to employ a receiver that is designed to use whichever signal is the stronger at any time, or to use the combined signals, or to switch from one to the other when the signal drops below a certain threshold. By using receiver diversity in this way, some of the problems introduced by multipath can be avoided by using appropriate coding at the transmitter, together with complex digital processing techniques at the receiver. It is possible now to resynchronize signals which have propagated along different paths and hence improve the recovery of data, even when there is a considerable amount of fading and interference. Another diversity technique is beam steering. In this technique, using multiple transmitting antenna for a single data stream can also be of benefit. So in the previous case, receiver diversity, we have two receivers. Here we have multiple transmitters and not receivers. So for example, by adjusting the relative amplitude and phases of the transmitted signals in two or more antennas, transmitter antennas, so it is possible to ensure that they are constructively interfere at the receiver rather than cancel. This is called beam steering and can be continuously adjusted to adapt to changing propagation conditions. The technique effectively increases antenna gain and can make a significant improvement to the range of transmission. The most important technique used nowadays, comparing to the two previous ones, is MIMO, multiple input, multiple output. So here we are combining multiple transmitting and receiving antennas. We can have, for example, 2x2 MIMOs, 2 transmitting and 2 receiving MIMO, 3x3 MIMOs, and so on. A key aspect of MIMO is to transmit different data from each transmitting antenna. So we are transmitting different data. We are increasing the capacity of transmitting data using MIMO. So either by splitting a data stream between them or by using data from independent sources. Each antenna is transmitting different data but on the same frequency channels as the other antenna. So using the same channel, we are trying to send more data. So we are increasing the capacity of data transmission using the same frequency channel. Transmitting multiple data streams with a single antenna would give two mixed up data streams. Using multiple separated transmitting antennas, one for each data stream, means that in a multipath environment, the different signals will tend to propagate along different paths involving different reflections and so on. Each of the receiving antenna then receives a different combination of these different signals. So another key aspect of MIMO is the need to have a considerable amount of digital processing at the receiver so that the data from each of the two transmitted signals can be recovered individually. This is illustrated in the following figure, where in part A we have a multipath environment. We have a space wave received as a receiver that requires processing for recovering the data transmitted by T1. In part B we say that we can add the digital processing at two receivers instead of one receiver to regenerate the data sent by two different sources instead of having one. And of course, in this case, we are increasing. We need more processing, and hopefully that the current evolution in electronic circuitry and in digital processings has helped these researchers to develop MIMO. And in the following scenario, we have 2x2 MIMO. Okay, since we are using two transmitting antenna and two receiving antenna. Basically, the net effect in a MIMO system is to allow twice or more as much data to be sent along the same radio channel as we have said. than is possible if only one antenna is used at each end. The reason that this can be achieved is because of the presence of multipath nets. MIMO does not work effectively when there is a clear line of sight, of course, because they will interfere among each others because they are using the same channel.